Hey everybody, I'm Bill Kinney. Welcome to video number 2 on what I think is the most beautiful subject in math, complex numbers and complex analysis. In these videos, we're going to emphasize 3 things: exploration, discovery, and then joy in discovery. I really want to encourage comments, and I'll try to reply to those that come in during the first day. If you like this content, please like, subscribe, and share it with your friends. In video 1, we looked at powers of I and how they formed a cyclic group. Here in video number 2, I want to look at what are complex numbers symbolically and graphically. How do you visualize them? This is pretty basic content, but it's also really fundamental. Let's take an example. A complex number is typically denoted by the letter Z in complex analysis. Let's take a complex number Z to be 4 plus 3i. So what you see here is you've got a real number, in this case 4, plus another real number times I, the imaginary unit. I is, as we saw in video number 1, defined by the property that it equals I squared equals -1. This leads to all sorts of amazing applications and interpretations. It's important to get some terminology down here. The real number that is not next to the I is called the real part of the complex number. And the real number that is next to the I, the 3 in this case, is called the imaginary part. That terminology is pretty important if you want to make progress in complex analysis, and it's also important to emphasize that both the real part and the imaginary part of a complex number are real numbers. What distinguishes them is that the real part is not next to the I and the imaginary part is next to the I. You can rearrange these things. You can write this as 3i plus 4. If you do so, it's still the same complex number. 4 is still the real part and 3 is still the imaginary part. But we'll most typically put the real part first and then plus the imaginary part times I. Notationally, we also use the following symbolism. RE of the complex number Z is the symbol for the real part. So for this particular example, RE of Z is 4, and IM of Z is the imaginary part of the complex number Z. IM of Z is 3. Again, the real part is the real number 4, and the imaginary part of this complex number is the real number 3. We use this notation very often. It's a very natural thing now to plot a complex number in a plane. After all, it's determined by 2 numbers. We associate the complex number 4 plus 3i with the point whose rectangular coordinates are 4, 3. And it is important that it's in this order. The real part is the first coordinate and the imaginary part is the second coordinate. We don't want to associate the complex number 4 plus 3i with the point whose rectangular coordinates are 3, 4. Once we've made this association, then it's very natural to plot the complex number 4 plus 3i as a point in the plane whose coordinates are 4, 3. So go ahead, and if you have got graph paper, that's great. I don't have graph paper, so I'm drawing it. I'm marking off on the horizontal real axis 4 spots to the right, and on the vertical imaginary axis 3 spots up. I see where this vertical line here at the real part equaling 4 and this horizontal line at the imaginary part equaling 3 intersect. That point right there is our complex number Z equals 4 plus 3i, again corresponding to the point whose rectangular coordinates are 4, 3. We can plot plenty of other complex numbers in this complex plane. For example, if we have another complex number, I'll call it W equals, say, -2 plus I. That is the same as I minus 2, but as far as plotting it goes, we want to associate this with the point whose rectangular coordinates correspond with the real part in the first coordinate, -2, and the imaginary part in the second coordinate. There's an I here, but realize that means it's 1 times I. The second coordinate of this point is going to be 1. Go 2 to the left on the real axis and 1 up on the imaginary axis. See where this vertical line and this horizontal line intersect. That's the point W equals -2 plus I right there. Graphing complex numbers as points in this complex plane is going to be super helpful for a lot of things. It's going to be helpful for the arithmetic of complex numbers. It's also going to be helpful ultimately when we think about complex functions of a complex variables and thinking of them as what are called mappings or transformations of this complex plane to itself or to another version of itself. It's really, really helpful. It's also a pretty natural thing to do to not just think of complex numbers as points in this plane, but also think of them as vectors in the plane. For any point in the plane, you can have a natural association with what's called a position vector for that point, which is an arrow. Vectors are visualized as arrows going from the origin to the point. So if I draw an arrow like this, going from the origin, try to make it straight here, to that point, I can think of that as a vector associated with this complex number z equals 4 plus 3i. And if I draw another arrow starting at the origin and going to this point, I can think of that as an arrow or vector associated with this other complex number, w equals negative 2 plus I. You might wonder what's the benefit of that. We're going to see a benefit of this pretty soon when we talk about complex number addition and subtraction. It's basically the same as vector addition and subtraction, and vector addition and subtraction can be interpreted geometrically in very beautiful ways, very natural and beautiful ways that actually have applications, especially to physics. I'll also say that just notationally, sometimes vectors are written as points using coordinates. Sometimes they're written using what are called I hat and j hat, standard unit vectors in the plane. That could get a little confusing because I hat could be confused with the imaginary unit I, and to tell you the truth, j hat could be confused with what electrical engineers use for the imaginary unit. They actually call it j because they use the letter I for something else. I will probably most commonly think of vectors as column vectors. So the point 4, 3 as an ordered pair, I will often write as a column like that. And this point, negative 2, 1, I'll often write as a column like this. And the benefit of writing vectors in column form is that you can relate it to something called matrix multiplication. And that'll be helpful for some things, and computationally speaking and visually speaking, to relate this to what's called linear algebra. Let me also show you a little bit of notation. We use this funny looking C here with a vertical line there, or in books it's often written in boldface, to represent the set of complex numbers, the set of all complex numbers. This is something that I will use a lot. In what's called set builder notation, it's the set of all quantities or symbols or expressions of the form, say, x plus I times y, or I could write x plus y times I, where x and y have the property that they are any real numbers, such that x and y are elements of the real number system. This funny looking R right here with the extra line, or in books it's often bold-faced, represents the set of real numbers. Because we have this natural correspondence between complex numbers and points in the plane, represented in rectangular coordinates, we have a natural correspondence here between the set of all complex numbers and the set of all real points in the plane, often written this way, R2. That's sometimes people say R squared, but I say R2 here, representing the two-dimensional plane consisting of all points in the plane. And you can think of this in terms of their rectangular coordinates, the set of all ordered pairs of the form x comma y, where x and y vary over all real numbers. There's a natural correspondence between these, and you can even say that these two things are what are called isomorphic as vector spaces over the real numbers. If you don't know what that means, that's okay. I'll probably talk about it later. It's helpful for relating and understanding complex analysis in terms of actually multivariable calculus. We'll use multivariable calculus a lot to understand complex functions as well. Let me end this video by just showing you something in Mathematica. I showed a nice visual in Mathematica in video number 1, but here I actually want to show you, well, it includes visual, but it also includes symbols that you can use in Mathematica to represent complex numbers. So here I've got 4 complex numbers in Mathematica that I'm representing as z1, z2, z3, and z4. 4 plus 3i, negative 2 plus 5i, 1 minus 4i, and negative 3 minus 3i. Notice that I in Mathematica is represented with a capital letter. Capital I squared, for example, is negative 1. You also can use it with sort of a fancy looking I to represent the imaginary unit I. I can do escape, double I escape to make a fancier looking I, and see that if I square it, I get negative 1. I can enter these complex numbers, Mathematica has built-in functions called RE and IM that can, for example, find the real and imaginary parts of Z2. Z2 is negative 2 plus 5i. If I enter this, I get negative 2. If I enter this, I get positive 5. Yes, confirming that the real part of Z2 is negative 2. The imaginary part is 5. And there's then two ways I can plot this. A built-in function called ComplexListPlot will plot the complex numbers Z1 through Z4 here. I can enter this to see that plot. I've also added some extra commands here that are for formatting things in a nice way, to label the axes, for example, and color things. ReIm converts a complex number to what's called a list in Mathematica. And once you've got something as a list in Mathematica, you can use something called ListPlot to plot those as actual points in a plane as well. So you can see I'm using ReIm for Z1 through Z4 here as well to essentially get the same plot, though I have labeled the axes X and Y instead of RE and IM to emphasize that maybe I want to think of this as a real plane instead of the complex plane. This is basic stuff, but again, it's fundamental for understanding complex analysis. I hope you enjoyed it. And I end, as my dad always said, strength and honor. Be strong, but also honor all people. We'll see you with video number 3.